What if the planet beneath your feet changed and the change was real, measured, and still not fully understood? Between 2010 and 2020, scientists began noticing something unusual. Several parts of Earth that usually behave in a slow and predictable way started to shift. These were not guesses or computer simulations. These were direct measurements taken using precise instruments across the world. Let us simplify this. Think of Earth as a well-built machine with many moving parts. Deep inside, there is a solid inner core. Around it is a liquid outer core that helps generate Earth's magnetic field. At the surface, we have oceans, ice, air, and the rotation that gives us day and night. Normally, each of these parts changes very slowly, almost like a clock that loses a second over many years. But in just one decade, multiple parts of this machine behave differently. The inner core changed how it moves. The magnetic North Pole started drifting much faster than before and moved toward Russia. A weak region in the magnetic field grew larger. Most surprisingly, Earth began spinning slightly faster, making days a tiny bit shorter when measured with atomic clocks. Now, here is why this matters. These systems are usually independent. It is like different departments in a large organization working separately. But suddenly, all of them showed changes at the same time. Scientists identified 7 major systems that shifted: the inner core, outer core, magnetic field, ice sheets, ocean circulation, atmosphere, and Earth's rotation. To understand the seriousness, consider a more precise scenario. Imagine a network of highly sensitive instruments in a research laboratory. One sensor measures temperature, another measures pressure, another tracks vibration, and another records electrical activity. Each is designed to operate independently, and small variations are expected. But if all of them begin to drift at the same time, even slightly, scientists do not treat this as coincidence. They begin to suspect that the underlying system, perhaps the energy supply or structural stability, is changing in a coordinated way. Earth is behaving in a similar manner. Multiple independent systems are showing shifts together, which suggests that deeper processes may be linking them. This leads to an important teaching insight. When independent systems change together, scientists begin to suspect that they may be connected by a deeper process. Something inside the system may be redistributing energy or changing how parts interact. The challenge is that we do not yet fully understand what that process is. There is no single explanation that connects all these changes clearly. Now consider the future impact. Even small changes in Earth's rotation can affect timekeeping systems like GPS, banking networks, and communication systems. Changes in the magnetic field can increase radiation exposure for satellites and astronauts. Shifts in ice and ocean circulation can influence climate patterns and sea levels. These are not immediate disasters, but they are early signals. They tell us that the baseline of Earth, the normal behavior we depend on, may be shifting. To understand why this is so unusual, we must first look at what scientists long believed about Earth: that it is mostly stable over human timescales. To understand why these recent changes are so significant, we must examine a long-standing assumption in Earth science that the planet behaves in a stable and predictable manner over human timescales. For most of recorded history, this assumption held true. The length of a day, defined as 86,400 seconds, remained effectively constant when measured with increasing precision. Modern systems rely on atomic clocks, which track time with extraordinary accuracy, while organizations such as the International Earth Rotation and Reference Systems Service continuously compare atomic time with Earth's actual rotation. The difference between the two was small, gradual, and manageable. Over decades, Earth's rotation was known to slow slightly, primarily due to tidal interactions with the Moon. The effect was measurable but predictable. A few milliseconds per century was the expected rate of change. Deep within the planet, similar stability was observed. The magnetic field, generated by the motion of liquid iron in the outer core, maintained a consistent global structure. It acted as a shield, deflecting charged particles from the Sun and preserving conditions necessary for life at the surface. The inner core, composed mainly of iron and nickel, rotated slowly within this fluid layer. While its motion was not directly visible, indirect measurements suggested a steady and continuous behavior. Geological evidence further reinforced this picture. Large-scale changes did occur, but only over immense timescales. Magnetic reversals, where the north and south poles switch places, unfolded over hundreds of thousands of years. Changes in rotation were similarly gradual. Even smaller variations followed clear patterns. One example is the Chandler wobble, a slight shift in Earth's axis of rotation. It behaves like a subtle oscillation repeating over predictable intervals. Such motions were studied, modelled, and understood with high confidence. This leads to an important teaching insight. Scientific systems are considered reliable, not because they never change, but because their changes follow consistent patterns that can be measured and predicted. Modern infrastructure was built on this reliability. Navigation systems, satellite communication, climate models, and timekeeping standards all assume that Earth's fundamental behavior does not shift abruptly. This is why the recent observations are not simply interesting anomalies. They represent a deviation from a framework that has been validated for decades, and in some cases, centuries. When a system long considered stable begins to show unexpected variation, the first response is not alarm, but careful verification. Instruments are checked, methods are reviewed, and independent measurements are compared. And it was during this process of verification that a pattern began to emerge. The deviations were real, they were measurable, and they were not confined to a single system. This brings us to the next question. If Earth was expected to change slowly, what does it mean when one of its deepest components begins to behave differently within a single human lifetime? This raises a deeper question. If Earth was expected to change gradually, what does it mean when its innermost region begins to alter its motion within a few decades? At the center of the planet lies the inner core, a solid sphere composed primarily of iron and nickel. It exists under extreme pressure and temperature, conditions so intense that direct observation is impossible. Our understanding comes indirectly through seismic waves generated by earthquakes. These waves travel through Earth and carry information about its internal structure. For many years, scientists interpreted this data to suggest that the inner core rotates slightly faster than the rest of the planet. The difference was small but consistent enough to support a stable model. The core was thought to move steadily, influenced by interactions with the surrounding liquid outer core. However, this assumption was challenged by new analyses. In 2023, researchers Yi Yang and Xiaodong Song examined decades of seismic records. By comparing how similar earthquake waves traveled through the inner core over time, they detected a subtle but consistent change. Around 2009, the rotation of the inner core began to slow. This alone would have been significant, but the data indicated something more precise. After slowing, the inner core did not simply stop adjusting. It began to move in the opposite direction relative to the surface. A useful way to understand this is to think in terms of relative motion. The surface of Earth continues rotating eastward. If the inner core begins to rotate more slowly than the surface, or slightly westward relative to it, the effect appears as a reversal when measured from above. Further evidence strengthened this conclusion. In 2024, Wei Wang and John Vidal conducted independent analyses using different datasets. Their results aligned with the earlier findings. The inner core was no longer maintaining its previous rotational behavior. This leads to an important teaching insight. In geophysics, conclusions are rarely based on a single dataset. When independent methods produce similar results, confidence in the observation increases significantly. The implication is clear. The center of the Earth, long assumed to be stable on human timescales, has changed its motion within a period we can directly measure. This is not merely a localized adjustment. The inner core interacts continuously with the outer core through gravitational and electromagnetic forces. Any change in its motion alters how energy and momentum are distributed within the planet. The next question, therefore, is not only what changed, but how that change propagates outward. Because rotation was only the first signal, evidence soon suggested that the structure of the core itself was also evolving. If the change in rotation suggested a shift in motion, the next set of observations pointed to something more fundamental, a change in structure. By 2025, researchers analyzing high-resolution seismic data began to detect subtle variations that could not be explained by rotation alone. The signals indicated that the surface of the inner core was not behaving as a rigid, unchanging boundary. Instead, it appeared to be undergoing deformation. To understand this, we return to how seismic waves are used. When an earthquake occurs, waves travel through Earth and are recorded by instruments across the globe. The time these waves take and the way they scatter or refract reveals details about the materials they pass through. Even very small changes in structure can be detected through careful comparison over long periods. In this case, scientists observed that waves passing along similar paths at different times were arriving with slight but consistent differences. This suggested that the boundary of the inner core was shifting. John Vidal and his colleagues proposed a mechanism for this behavior. The inner core is surrounded by a turbulent liquid outer core, composed primarily of molten iron. This fluid is constantly in motion, driven by heat and rotation. The forces it exerts on the solid inner core are not uniform. As a result, parts of the inner core's surface may experience gradual displacement. This is not a sudden movement, but a slow, continuous adjustment under extreme pressure. A useful way to think about this is not as a rigid object breaking, but as a solid structure whose surface is being reshaped by persistent external forces. This leads to an important teaching insight. In extreme environments, such as the center of the Earth, the distinction between solid and fluid behavior becomes less intuitive. Materials can deform over time, even while remaining structurally solid. The implication of this deformation is significant. When the shape or mass distribution of the inner core changes, it affects how mass is arranged within the planet. In physics, even small redistributions of mass can influence rotational dynamics. Consider a system where mass shifts slightly closer to or farther from the axis of rotation. The rotation rate adjusts in response. This is a fundamental principle of angular momentum conservation. In Earth's case, these changes are extremely small in magnitude, but the system itself is large and sensitive. Over time, such internal adjustments can propagate outward, influencing the behavior of layers above. This creates a connection between deep Earth processes and surface observations. The inner core does not operate in isolation. It exchanges energy and momentum with the outer core, which in turn interacts with the mantle and surface systems. The key point is not that a single layer has changed, but that the interaction between layers has become more dynamic. And this interaction may provide a pathway through which deep internal changes influence something we can measure directly: the speed at which the entire planet rotates. Changes within the core alter how mass and energy are distributed inside the planet. The next question is direct and measurable. Can these internal shifts influence how fast Earth rotates? For a long time, the answer appeared straightforward. Earth's rotation was gradually slowing. This was not a theoretical assumption, but a well-established observation, supported by centuries of astronomical records and modern measurements. The primary cause was tidal interaction with the Moon, which transfers rotational energy away from Earth over time. The rate of this slowing was extremely small. On average, the length of a day increased by a few milliseconds per century. This change was so predictable that it became part of how global timekeeping systems were designed. However, beginning around 2016, high-precision measurements revealed an unexpected trend. Instead of continuing to slow, Earth's rotation showed signs of acceleration. Days became slightly shorter. The magnitude of this change is small but measurable. With atomic clocks, even microsecond-level variations can be detected and tracked. These instruments do not rely on Earth's motion. They measure time based on atomic transitions, providing a stable reference against which planetary rotation can be compared. When scientists compared atomic time with Earth's rotational time, a discrepancy emerged. The planet was completing its rotation slightly faster than expected. At first, researchers examined known surface factors. Atmospheric circulation can redistribute mass and affect rotation. Ocean currents can do the same. Seasonal changes in ice mass also play a role. These influences were modelled and accounted for. Yet even after including these effects, a residual remained. The observed acceleration could not be fully explained. Leonid Zotov and other researchers confirmed that the source of this residual is still unknown. This is a critical point. In geophysics, unexplained residuals often indicate that an important factor has not yet been identified or fully understood. This leads to a teaching insight. When a system behaves differently than predicted and known variables fail to account for the difference, the model itself must be re-examined. One possibility is that processes within Earth's interior, including the changes already observed in the core, are contributing to this acceleration. If mass distribution shifts even slightly toward the axis of rotation, the rotation rate can increase. This follows directly from the principle of angular momentum conservation. The implication extends beyond physics into practical systems. Modern infrastructure assumes that Earth's rotation slows over time. This assumption is built into how time is adjusted globally. If the trend reverses, even temporarily, it creates a situation that existing systems were not designed to handle. This brings us to a fundamental consequence. The measurement of time itself, something we treat as constant and reliable, is directly linked to the behavior of a planet that may no longer follow its expected pattern. The consequence of a changing rotation is not abstract. It directly affects how we measure and coordinate time across the entire planet. Modern civilization depends on a precise and shared definition of time. This is not based on Earth's rotation alone. Instead, it is anchored in atomic clocks, which measure time using the consistent behavior of atoms. These clocks are extraordinarily stable and do not vary with planetary motion. However, daily life is still tied to Earth's rotation. A day is defined by the planet completing one full turn relative to the Sun. When these two systems, atomic time and rotational time, begin to drift apart, adjustments are required. Since 1972, this adjustment has taken the form of leap seconds. When Earth's rotation slows slightly, an extra second is added to keep clocks aligned with the planet's position. This process has been manageable because the trend was consistent and predictable. The recent acceleration introduces a different problem. If Earth begins to rotate faster than atomic time, alignment would require removing a second instead of adding one. This is known as a negative leap second. At first glance, removing a single second may appear trivial. In practice, it presents a complex challenge. Many global systems are designed to handle the insertion of time, but not its removal. Software, databases, and communication protocols often assume that time moves forward in uniform steps. Consider systems that rely on exact sequencing. Financial transactions, satellite navigation, and distributed computing networks all depend on synchronized timestamps. If a second is removed incorrectly, it can create inconsistencies in data ordering, leading to errors that propagate across systems. A useful way to understand this is to think of time as a reference grid used by independent systems. If the grid shifts unexpectedly, even by a small amount, systems that rely on precise alignment may temporarily lose synchronization. This leads to an important teaching insight. Stability in measurement systems is not only about accuracy, but also about predictability. When the underlying reference changes in an unexpected way, the complexity of maintaining coordination increases significantly. Recognizing this, international authorities made a notable decision in 2022. They agreed to phase out leap seconds entirely by 2035. This decision was not based on solving the underlying physical changes, but on reducing the operational risk associated with managing them. In effect, timekeeping systems are being adapted to tolerate a growing difference between atomic time and Earth's rotation. This marks a shift in approach. Instead of forcing perfect alignment, the system accepts a controlled divergence. While this adjustment addresses timekeeping, it does not explain the underlying cause. The question remains, why is Earth's rotation behaving differently? At the same time, another observable system, one that also originates deep within the planet, has been undergoing significant change. While timekeeping systems adjust to a changing rotation, another signal of deep Earth activity becomes visible at the surface, the movement of the magnetic North Pole. Unlike geographic poles, which are fixed by Earth's axis of rotation, the magnetic poles are determined by the structure of the magnetic field. This field is generated by the motion of liquid iron in the outer core, making it inherently dynamic. However, for much of recorded history, this movement was slow and predictable. The magnetic North Pole was first precisely located in 1831 by James Clark Ross in northern Canada. For more than a century, it drifted gradually across the Arctic region at a modest pace. This slow movement allowed scientists to model its trajectory and update navigation systems without difficulty. A significant change began in the late 20th century. By the 1990s, measurements showed that the pole's Getty had increased noticeably. What had once been a slow drift became a rapid displacement. By 2025, the magnetic North Pole had crossed from Canadian territory into Russia. At its peak, its Getty reached approximately 55 kilometers per year, a rate far higher than historical averages. To understand why this matters, consider how magnetic navigation works. Compasses align with the magnetic field, not the geographic poles. Aviation routes, maritime navigation, and even some satellite systems depend on accurate models of this field. When the pole moves faster than expected, these models must be updated more frequently. This leads to an important teaching insight. A system can remain functional while its underlying parameters change, but the cost of maintaining accuracy increases. In this case, global navigation systems require continuous recalibration. The cause of this accelerated drift is linked to processes within the outer core. The magnetic field is shaped by the flow of molten iron, which creates complex and shifting patterns. Changes in this flow alter the distribution of magnetic forces, effectively pulling the pole in different directions. However, the exact mechanism behind the recent acceleration is not fully understood. Multiple hypotheses exist, including changes in core flow patterns and interactions between different magnetic regions, but no single explanation has been confirmed. What is clear is that the magnetic field is not behaving in the steady manner once assumed. Its changes are measurable, rapid, and closely tied to the same internal dynamics that are affecting other Earth systems. This observation does not stand alone. While the pole's movement has recently slowed, another feature of the magnetic field has been intensifying, and it is this feature that provides a more localized but equally important indication of instability within Earth's core. The changes in the magnetic pole indicate a shifting system, but they do not reveal where that instability is most concentrated. For that, scientists examine a specific region where the magnetic field has weakened significantly. This region, known as the South Atlantic Anomaly, extends across parts of South America and the South Atlantic Ocean toward Africa. Unlike the gradual movement of the magnetic pole, this anomaly represents a localized reduction in magnetic field strength. To understand its significance, recall that Earth's magnetic field acts as a protective barrier. It deflects high-energy charged particles coming from the Sun and from deeper space. Where the field is strong, this shielding is effective. Where it weakens, more radiation can penetrate. The South Atlantic Anomaly is one such weakened zone. Over the period from 2014 to 2026, measurements from satellite missions, including those conducted by the European Space Agency, showed that this region expanded and became more complex in structure. Instead of a single uniform weakening, the anomaly began to display multiple zones of reduced field strength. These zones interact, shift, and evolve over time, indicating that the underlying processes are not simple or uniform. A practical consequence of this can be observed in satellite operations. Spacecraft passing through this region experience higher levels of radiation. Sensitive onboard electronics are more likely to register errors, and in some cases, systems are temporarily shut down as a precaution. Astronauts traveling through low Earth orbit have also reported brief visual phenomena, often described as flashes of light. These are caused by high-energy particles interacting directly with the human visual system. This is not a failure of equipment, but a direct effect of increased radiation exposure. This leads to an important teaching insight. The magnetic field is not only a geophysical feature, it is an active shield that directly influences technological systems and biological experience in space. The existence of the South Atlantic Anomaly suggests that the processes generating Earth's magnetic field are uneven. The outer core does not produce a perfectly symmetric field. Instead, it generates regions of varying strength, shaped by complex fluid motion. As these internal flows change, the structure of the magnetic field adjusts accordingly. The anomaly can therefore be understood as a surface expression of deeper turbulence within the outer core. What makes this particularly important is not just its presence, but its evolution. The expansion and fragmentation of the anomaly indicate that the magnetic system is becoming more dynamic over relatively short timescales. This observation aligns with earlier findings. Changes in rotation, shifts in the inner core, and movement of the magnetic pole all point toward increasing variability within Earth's internal systems. The key question now is whether these are isolated phenomena or part of a coordinated pattern. To answer that, scientists began comparing data across different fields, looking for connections that might reveal a larger structure behind these changes. These observations, when considered individually, suggest localized changes, but when scientists began to compare them across disciplines, a more structured pattern emerged. Researchers working in geophysics, climatology, oceanography, and atmospheric science were not initially studying a single unified problem. Each field used its own instruments, data sets, and methods. Yet when their results were placed side by side, a consistent trend became visible. Multiple Earth systems had deviated from their expected behavior within the same decade. These systems include the motion of the inner core, variations in the magnetic field, changes in surface rotation, loss of ice mass, shifts in ocean circulation, alterations in atmospheric momentum, and variations in the Chandler wobble. Each of these systems operates under different physical principles. The inner core is governed by high-pressure solid-state dynamics. The magnetic field arises from fluid motion in the outer core. Ocean circulation depends on temperature and salinity gradients. Atmospheric momentum is influenced by global wind patterns. Under normal conditions, changes in these systems occur on different timescales and are often studied independently. The expectation is that their variations are loosely coupled, not tightly synchronized. However, the data suggests otherwise. When independent systems, measured using different techniques and observed by separate institutions, all show deviation within a narrow time window, the likelihood of coincidence becomes low. This does not immediately reveal a single cause, but it does indicate that the assumption of independence may no longer hold. This leads to a key teaching insight. In complex systems, simultaneous deviation across multiple subsystems often signals a transition in the overall state of the system. The system is no longer behaving in a steady or stationary manner. In statistical terms, Earth is being described as non-stationary. This means that its baseline behavior, the reference against which change is measured, is itself evolving. A practical implication follows from this idea. Models built on past data assume that future behavior will resemble historical patterns. If the baseline shifts, those models become less reliable. For example, long-term climate projections, navigation corrections, and rotational predictions all depend on stable reference behavior. When that stability changes, predictions require continuous revision. It is important to clarify that this does not imply immediate instability or catastrophic change. Instead, it indicates that the system is entering a phase where variability increases and predictability decreases. This distinction is critical. A system in transition is not necessarily unstable, but it is more sensitive to internal and external influences. The emerging picture is not of isolated anomalies, but of a coordinated shift across multiple layers of the planet. This raises a final question. Has Earth experienced such transitions before? And if so, what were the conditions during those periods? This pattern of simultaneous change leads to a broader perspective. The Earth we observe today may not be in a stable phase, but in a transitional one. Geological records provide important context. Over long periods, the planet has undergone shifts in rotation, magnetic field reversals, and major climate transitions. These events are not random. They tend to occur during intervals when internal and surface systems are actively adjusting. One of the most studied examples is the transition at the end of the last ice age. During that period, large-scale changes in ice mass, ocean circulation, and atmospheric patterns occurred together. The system did not move smoothly from one state to another. It passed through a phase of increased variability before settling into a new equilibrium. This leads to a key teaching insight. Stable states are easier to describe and predict, but transitions are where systems are most sensitive. Small influences can produce larger effects because the system is already adjusting. Today, human civilization operates on the assumption that Earth's fundamental behavior remains stable over short timescales. Timekeeping systems assume predictable rotation. Navigation systems rely on stable magnetic models. Climate projections are built on historical patterns. These assumptions have been valid for decades, supported by consistent observations. However, The recent measurements suggest that some of these underlying conditions may be changing. It is important to approach this carefully. The presence of change does not imply immediate disruption. The systems we rely on continue to function, and many variations remain within manageable limits. However, the concept of a fixed baseline is becoming less certain. We do not yet know what the new baseline will be. It may involve subtle adjustments that stabilize over time, or it may reflect a longer period of variability. The duration of such transitions is not easily determined, as it depends on processes occurring deep within the planet. What can be stated with confidence is that the measurements are consistent across independent observations. The inner core has altered its motion. The magnetic field is changing in structure. The rotation of the planet shows measurable variation. Surface systems are responding in parallel. These are not isolated anomalies. They form a coherent set of observations that indicate a shift in how Earth behaves as a system. The appropriate response is not speculation, but continued observation and refinement of models. As new data emerges, our understanding will improve, and with it, our ability to adapt. The central conclusion is therefore precise. The planet is changing, not in a distant geological future, but within a time frame we can measure directly. And understanding this change is no longer optional. It is necessary for maintaining the systems that depend on the stability we once assumed.